Okay, lovely people. This is going to represent a column. All I did was 2x4 material there. This will represent the concrete deck. There are 2 nails. That represents top and bottom rebar reinforcement. This should be the most simplest way to explain it to you. Here's the rebar going into the deck. This would be the column, or it can be the wall turned down with 2 pieces of rebar, one going up and ultimately going from here to there. But I'm taking some liberty, anchored it back here. That is the back of the nail head is the anchor. Now, we'll apply a load out here. That will be our deflection load. And we shall see that it should come apart at the bottom. If we had an uplift load here, what would you see? Or down, if this was going down, what would you see? Well, if it was an uplift, it would be 2 different results. But if this was uplifting, you would see it open here, right? And if it was going, a car loading, for example, here, we would see it go down, and it would react what? Here. And this is the point of the other video I made to show you that it's acting as a fulcrum from this point, a fulcrum, and this is just acting like a giant lever. Your pry bar, your lever, right? Your deck's going down, acting like a lever against the rebar. So let's start separating it. Sorry, I didn't. It's going down. So now it's got a downward direction, trajectory, if you will. See it? That's an exaggeration, but you see what's happening here. Now, at some point, see how this? It's not. They're not equal. These 2 ends do not react equally. This part here becomes your pry bar, your wedge, to start prying it. To start at the point of prying it, where you're prying, trying to do it without over exerting and flying it off into the air. Cat hairs. Now, got this from outside too. So you see what's happening there? Your rebar is losing engagement. This acts as a prying effect here. It's a force multiplier, this corner. With the deflective mode, even though they allow for some deflection in AIC, AIC is not addressing this. When they do when you see them do testing on beams, they often have it freestanding, and it's on a roller or a semi-pin, but it's not anchored how it is in real life. In real life, it would be this. It would be that. And in real life, this becomes a force multiplier to make it easier to pull out at the top. If I would just try to grab this side and this side and pull it apart, I would equally be pulling on them. Equally pulling on them. But if I add my force multiplier, that is this fulcrum, and the pry bar effect, it just easily pries down and away. Notice how at the bottom again. So this is happening at this point. You're going to get a fracture. Now I'm going to show you why the columns, when they do that, they fail across the top. I'm going to build up the model for you, a model. So it shows that at one point it's weak at the top anymore and it can't hold. It just falls off on one side. 2 of the reinforcement bars stay across the top. I call them roach antennas, right? They come across the top like that. Roach antennas. That tells you the direction. If it were that side of it, well, that tells you the deck was pulled that side. But this side is pulled, you see it on this end. Sorry, I'm looking at the camera trying to talk to you. So it's pulled on that end. So your antennas come off here, off the top. But in this case now, let's use the same beam, and I want you to visualize it by the parking garage. Why do we see that concrete in there? Simple. It's all the dead load of the structure above compresses and leaves that concrete in place as this action is taking place, as the failure of the deck around it is taking place. We are left with the reveal of the concrete between the upper column and bottom column because it's compressed and locked in by the load of above. And the reaction and forces that happen were not enough to do any more than, actually it locked in that rebar going across the antennas and held it in place, and that's why we see it there. And the other ones we see obviously the antennas have to pick a side, or pick 4 sides. If you're going to do sides, it could have been diagonal also, but they picked the west and east direction. So Again, the force multiplier becomes the deck. Does become this point location here. And there's our hinge. It becomes whatever you would like to think of about as a hinge, as a pry bar effect, as a fulcrum, however you can get to it in your brain to get to this point to see that this compressive moment here is not just, as ACI and demonstration will show you, it can take this much in compression and tension. But when the system's together, a little bit down here equals a lot down up here. A lot more up here on ripping the rebar failure mode at the column location. At the column location. So that's because they're columns, not wall. So talking to someone else who wants me to explore the wall, you tell me if the deck dips and you've got 50 pieces of rebar over there that are holding like this versus one column with 2 pieces of rebar holding like this, they're opposing each other. Which one is greater in strength? The one that's only got 2 bars or the one that's got 50 lined up? I go with the 50. And that's why I don't have that wall, even though the dip could possibly be the same, although the deflection would be, this is mid-span deflection or deflection somewhere, and I can actually move the deflection in off the negative steel point. So negative steel, let's just jump to that. So up here, now I want to add what I call the negative steel moment, right? This will help hold this, maintain this from doing that dip down. So now we'll use my arm. I'm going to grip over here, put this against my stomach, and now I'm going to push. When I do that, my arm is holding it back, capturing the load back in here. But look where it's, let me do that. That way you can see it. So right here as I try to pry down, and I'm levering it against my belly too. So as I try to pry down, this one takes on the force now. And remember, it's tied back to here, not in a bracket capacity like I just made. I just couldn't do that. So it's tied back to here. The has to resist that action, that force multiplier to want to pull it out with that little bit of deflection. That's your steel up top, the negative steel, negative moment steel, right? Negative to capture it, to stop it from wanting to rotate over. But they see it as the deck just dipping. They don't see it as this right here, this compressive moment here. Now the deck has another one on the other side of it. If this starts pulling out, the other side might start slipping also because they were engulfed across each other. If one starts rotating, it starts breaking the bond between the deck that's across from it. That's why I like T-beams for the parking area, or just regular beams in general would help. Much better than running it on top, as ACI will allow, putting your deck with a 9.5-inch slab above it, for example, with that span that says that resists punch shearing. Which brings us to the last topic of this short video. And I'm taking liberty to say short, aren't I? So the punch shearing, let's look at this, grab this magazine. Critical shear area. This is a connection magazine. Let me hide my connection. It's for rebar, for steel connectors. You guys could probably grab a copy of it. Putting your people first. It's bridges and steel. So now, look. We have this over here. The critical shear area is the extra steel they add up there to try to reinforce this so it doesn't punch down around it, right? It doesn't punch down around around it. Let's grab a page out of the book that's going to sacrifice itself for us. So now, this would be the critical shear area where they build up the extra reinforcement and then go over to the tributary area, the area from this area to the next critical shear area and then to the column. And they don't use extra reinforcement to get over to there besides here. So think about it. They're saying the loads are going to be greater in this critical shear area, this extra piece. But only here is where we need to resolve it because it's going to want to pull down around the column. So let's make this really strong. And then you look at the images of punch shearing online and you see things that look like this. Where some of them look stripped down like that. And then some will look like that. We've seen that where you see this capital, if you will. It's not a capital, it's part of the deck. The capital will be the part that's under here holding it. It's the critical shear area. That's the extra reinforcement. Why did it stay and the other deck went around? Because this was so rigid, so much extra steel, same thickness as the deck, slab, same thickness, that when the deck deflected, instead of being deflecting back here now and driving down like I showed you here, it now has, this is so built up, so, well, good, if you will, stiff, that the deck is deflecting, out here at my elbow, it's deflecting, but now look the point, the moment is out here. Look, see it? See my elbow turn? And the moment is out here. No longer is it here, where it's the weakest. When this deck deflects, it says, oh, we've run up against something that's not bending. And so it says, we'll take it here then. And this is where it bends, and then ultimately it gets so much bending. Remember, the rebar is still going to pull out. It's still going to do what it did here. When it bends down, it's the force multipliers underneath. You'll see some spalled concrete there perhaps beforehand. The dip and the compression and the spalled concrete. It will then kick out and break free as it breaks the rebar connections. Hold on, I got a cough. Excuse me. So, so then we're over here. So then we're at this, when you see that punching looks like that. When it looks like this, with just a sleeve, it was just all deck. There was no extra critical shearing and reinforcement there to resist and even make one of these deals like you see in that one parking garage. The failure in the UK, maybe, I don't know where it is, but it looks like that. And that's because this deflection came apart up to this section, and this was able to resolve it, hold that force, resist it, and make the moment here because of the larger reinforcement area. And again, when you see it just like this, automatically you can say, oh, that wasn't that draped here, and that's where it came down. That it made it over here, so automatically you can just pretty much think, okay, they didn't have a strong critical shear area there. It didn't resist, or something was defective in that zone. Because when these things fall, when they fail, they should not. They ideally, if you want to see a good critical shear area, it will be in place. Now there's a point to be made about too rigid, and once it's too rigid, if the deck is flexing like that, it's going to weaken this section right there where this is not flexing anymore, and that's where you're saying the rigidity is what you created an issue for, and you get a brittle fracture. And what's the difference? Breaking, brittle fracture here, or brittle fracture here? Both of them equal failure. The difference in inspecting for cracks, are you going to look by the column, and if you see cracks out here propagating from the critical shear area, you now know that you've got a strong critical shear area. If you see cracks propagating up to your column, you now know your critical shear area in the slab is about the same reinforcement, reactive ability. It's flexing all the way up to the deck. In our Champlain Tower South, it appears by the cars that we have cracks up to a column. So it's telling you that the whole deck is flexing and the cracks are representative, and that's where I'm going to leave this video. Take care.